All right, so as we begin our first unit, this first unit is going to be on sequences and series and a couple of different applications and extensions of them. If you look over here at our essential questions for the unit, there's three main questions that kind of give us the three big topics in our unit. How do patterns of numbers progress? That's the different kinds of sequences that we're going to be dealing with. There's lots of different patterns, okay? But then also, building on that, how do we prove different relationships inductively? Looking at inductive reasoning and a process of proving things called math induction, which is a really neat process once you get the hang of it. And then finally, how is the binomial expansion useful? We're going to learn about the binomial expansion. You guys have probably used Pascal's triangle before.
Yeah.
Okay. We're gonna build on that. Look at adapting what we know about that and the binomial theorem to kind of some other contexts. One being like probability, and then kind of looking at some different applications and such for that. So that's kind of where we're headed. I want to start though just by talking about what a sequence is and making sure that we all understand the notation that we're going to be using. Okay, there's some notation that it's important you understand, or else some of the other things that we're going to do, especially when we get to math induction, it's not going to make a whole lot of sense. All right, so the first thing here we'll look is just the definition of what a sequence is, and then talking about the definition of a sequence. If you're given a sequence and asked to find the definition of a sequence, what are we talking about? Okay, so you can see here a sequence is a function whose domain is the set of positive integers. The function's values are given as a sub 1, a sub 2, a sub 3, and so on to some generic one called a sub n. All right, and again, what I'm saying there, get the pencil. The way I'm reading that would be a sub 1, okay? That's just short for subscript. So a sub 1, and when you see that number next to the a, or in some cases people will use u's, depending if you look it up online or something like that. I think IB actually uses u's. It really doesn't matter. But the number tells you which term in the sequence it is, and it also tells you what n equals for that term. Okay? So, in this case, for a sub 1, n equals 1. It is the first sequence, the first term in the sequence. Okay? First term of the sequence. And also n equals 1. Okay? Can everyone see that well, or do we need to hit the lights? Can anyone see that all right? Yeah. Okay, we'll leave it. Now, the definition of a sequence is an equation, all right? It's an equation that defines a sub n, all right? A sub n. And it'll do it in terms of the variable, the independent variable, n. Okay? That's why it's important to notice for each term what n equals, all right? So someone just give me 5 numbers that are in some kind of a pattern.
2, 4, 6, 8, 10.
All right, 2, 4, 6, 8, 10. All right, we're counting up by 2s. All right, so that's a sequence. Okay, that's a sequence. Now, for each of these terms, we could say a sub 1 equals 2, a sub 2 equals 4, a sub 3 equals 6, A sub 4 equals 8, and A sub 5 equals 10. Now just thinking about this logically, is there some way that you could generalize this to relate the value of n in each case to the value in the sequence?
Yes.
What?
Like a sub n equals to 2.
Yeah, that's right. Okay, a sub n we could say equals 2n because here's n, that's 1, and the value ended up being 2. So it was 2 times 1. Okay? A sub 2, n equals 2, it's 2 times 2. So you see here the value of n is changing to match the number of the term. Okay? It's really important that you understand the notation that we're dealing with here.
So n equals the number of the term.
N equals the number of the term, that's correct. Okay. So that's what we're talking about. If you're asked to find the definition of this sequence, they're not asking for something like this up here. They're asking for an equation. A sub n equals whatever it is. Okay? All right, now, there's a number of different kinds of sequences. We're going to look at 3 main ones. We're going to look at arithmetic and geometric sequences, which are particular kinds. But the fact of the matter is actually that every sequence could be written as a recursive sequence. Okay? Now, is there anyone, maybe you've done some stuff with computer science before, who's dealt with recursion? Have you ever dealt with recursion? No? A little bit? Okay. What's the basic gist? Can you explain it?
Depends on the term before it.
Okay, yeah. You're in computer science, you could write a function where if you need to figure out what the value of that function is for a certain value, it actually has to call a new instance of itself and pass something into it, and then it might have to call another instance of itself until it gets down to this one that's predefined, and then it'll kind of backfill all of it. And if that makes no sense, that's okay. Take some computer science classes and you might use that.
It's kind of like conditionals.
Okay?
Computer science.
Oh, like the ifs and that kind of thing? Yeah, or like a loop.
Yeah.
Yeah, it's kind of like it's creating a loop there. Where each value is dependent on the previous one. In a sequence, we're defining a term based on what the previous term equaled. Okay? Now, looking back on the example that we had before, the 2, 4, 6, 8, we would say its explicit definition was a sub n equals 2n. We could have also defined it recursively. Now, the explicit definition is better if we can figure it out. Okay? So if we were going to do this, we would use the a sub n equals 2n, because if we wanted, we could find a sub 100 really easily, right? What's a sub 100? 200, all right. Now, if I were defining that same sequence, 2, 4, 6, 8, 10, recursively, I would have to first of all define what a sub 1 is. The definition of a recursive sequence gives the first term, sometimes more than that, but we would have to say, okay, a sub 1 is 2, and then every other term, a sub n, is going to be the previous term. How do you think we could write that?
A sub n minus 1.
Very good. A sub n minus 1 plus 2. Okay? Now notice that n minus 1 is in the subscript. So if I'm finding a sub 5, I need to take a sub 4 plus 2. Okay? Because 5 minus 1 is 4. Now, what would the downside be to trying to use this to find a sub 100?
You always have to like figure out the previous term.
Yeah, we'd have to find out the previous 99 terms in order to find out the 100th term, okay? Because we'd have to know what the 99th is, and the 99th you'd have to know what the 98th is, and so on, all the way down until we got to 1, okay? So this is a recursive definition of this same sequence, and since we know this, we would prefer to use that explicit definition, okay? Does that make sense? Anyone have any questions so far? Okay? Alright, now, one very famous example of a recursive sequence that you've probably heard of before, you may have heard of before, is the Fibonacci sequence, okay? You may not have known that it was a recursive sequence, but you've probably heard of that sequence, alright? Notice the definition. Here, we're told what a sub 1 and a sub 2 are. Okay? And the reason that they tell us both of those is because the definition here is dependent on not just the previous one, but the previous two. Okay? So a sub n minus 1, that's the previous term. A sub n minus 2 is the term before that one. Okay? So, if I were to find a sub 5 here, what would I have to do?
Find out a sub 3 and a sub
Very good. A sub 3 and a sub 4, we'd have to add those together. Okay? Now, we don't know either one of those, so we now have to kind of go back even further, right? So, let's think about this sequence. If each term is the previous two added up, and this is a sub 1 and this is a sub 2, what's a sub 3? 2. 1 plus 1 is 2. How about what's a sub 4?
3.
It's 3. 1 plus 2 is 3. And how about a sub 5?
5.
It's 5. Okay? 2 plus 3 is 5.
Oh, because I was thinking 3 and 4. But it's not the term. No.
Yeah, no, I get what you're saying. Yeah, it's not the values of n, it's the actual values of the terms. Yeah, so 2 plus 3 is 5. And then finally, so now we actually know enough to be able to figure out what a sub 5 is, because we knew a sub 4 was 3 and a sub 3 is 2. So a sub 5 ends up being 5. And once you get the hang of these, it's actually really easy to get lots and lots more. Okay? But sometimes the notation can be a bit of a challenge. Alright. So, are there any questions about Fibonacci sequence? If you want some real interesting kind of exploration types of stuff, just do a quick search for Fibonacci sequence and the golden ratio. Okay? They actually have come up with an explicit definition for the Fibonacci sequence, and it uses the golden ratio, 1 plus radical 5 over 2, I think it is.
3.6.
I'm not sure what it is as a decimal. But if you've heard of the golden rectangles used in art and architecture and stuff, and the golden ratio, they've actually used that ratio to come up with an explicit definition of this Fibonacci sequence. That's kind of cool. So far we've looked at our basic idea of a sequence. We've looked at Fibonacci sequences. One other thing we want to look at as kind of an introductory aspect to sequences and series before we delve into specific ones further is dealing with factorials. Okay, this will show up in some of our sequences, but factorials, all right? How many of you have worked with factorials before? Okay, a couple? All right. If you haven't, that's all right. We're going to work with them right now a little bit, and then we're actually going to work with them even more in our second unit when we get into the probabilities, okay? So let's talk about what a factorial is. The notation, first of all, is this exclamation point, okay? Some number followed by an exclamation point. Now what we're looking for here, or what we're trying to do is, this is notation to represent multiplying every number from 1 up to the number we're taking the factorial of together, okay? So if we were doing, say, 8 factorial, well here, let's let you guys pick one. Pick a number 1 to 10.
7.
7, okay? 7 factorial. Alright, so if we're doing 7 factorial, according to our definition, we'd have to do 1 times 2 times 3 times 4 times 5 times 6 times 7. And I'm glad that we have this notation, because that would be really annoying to write out all the time, okay? Especially if we were studying, you know, probabilities and working with these a lot, okay? Now, you do all that multiplication, you know, 6 times 7 is 42, times 3 would give us 126, times 4, 126 times 4 is going to be 504, and then there's a 10, so 5040, okay? So that whole thing equals 5040. Now you might say, well, what is this for? Okay. Well, actually, this value right here is the number of different ways. If I had 7 objects and I wanted to put them in a specific order, that's called a permutation, we'll talk about in a sec. If I wanted to put all 7 of those objects in a particular order, I could do it 5040 different ways. Okay? Because if I had 7 spaces to put them in, 1, 2, 3, 4, 5, 6, 7, I'd have 7 different objects I could put in the first one, and that would leave me with 6 that I could put in the second one, and then 5, and then 4, and then 3, and then 2, and then I just have 1 left for the last spot. Okay? And then if I multiply all those together, that would be all the different possibilities, okay? We're going to delve into that a lot more in Unit 2, but I just want you to know where this is coming from, okay? But that's really what this factorial is. It's an arrangement of however many items we're looking at, okay? One definition to remember, if you ever end up with a 0 factorial, it equals 1. If it didn't, we'd mess up all of our formulas. We wouldn't be able to do half the stuff that we can do. Alright, so we define that as 1. Alright, one of the cool things that we can do with this, though, is reduce fractions. Alright, if I had asked you to, you know, here, find 18 factorial by hand, that would be really mean. But if we were doing, say, 18 factorial and we wanted to divide that by 16 factorial, there's actually a really easy way of doing that, okay? We know that 18 factorial is 18 times 17 times 16 times 15 times 14 all the way down until we get to 1, right? And we know that 16 factorial is 16 times 15 times 14 all the way down to 1. Well, look.
Is it just 18 times 17?
That's right, okay? This and this are identical. And you guys know when you have multiplication in the numerator and denominator of a fraction, you can cancel out identical terms. So the 16 over 16 is 1, the 15 over 15 is 1, and so on. Okay? So the nice thing is you don't have to write all this out. You could just say, okay, it's 18 times 17 times 16 factorial over 16 factorial. And now, hey, 16 factorial over itself is 1, so I just have to do 18 times 17. That's 153 times 2, is that 306? So I want to check that. Is that 306?
Yeah.
Is it? Okay. Good. All right. So, I want to take a moment here and I want to give you guys a chance to try one of these. Okay? Someone give me a 2-digit number.
33.
33, okay? 33. Let's say we had 33 factorial divided by 30 factorial, okay? Take a minute or two here and try that yourself.
Is this an app on the iPad?
Okay. Yeah, this is explain everything. So, all right, so what did we simplify 33 factorial over 30 factorial down to? What do we have?
32,000.
Oh, you got
32,736.
736. Okay, so the 30 factorial canceled stuff out, right? So what was left was just the 33 times 32 times 31. Okay? All right. So, try to get comfortable working with these, okay? It can make very, very large number problems much, much simpler, okay? If you put 33 factorial into the calculator, it may or may not even be able to handle it. At least not without using scientific notation. So, that's our basic idea with factorials. I mentioned the concept of a permutation already, okay? There actually are two things that I just want to introduce just to show you kind of that, yeah, this isn't just some random thing. These are used quite a bit. These two concepts are really at the foundation of an entire branch of mathematics called combinatorics. Basically, that's just a fancy term for learning how to count stuff. All right, combinatorics is the study of how to count stuff in mathematics. All right, but that combinatorics is also the foundation then of probabilities. Okay, if we can count how many times something could happen or how many different ways it could happen, then we can figure out the probability of it happening. All right, so combinations and permutations, I had mentioned that just the n factorial was how many different ways you could arrange n things, okay? These two formulas are kind of variations or extensions of that idea, okay? N factorial would arrange all of the stuff that we have. Well, if you look at this you could read as n permutation R, okay? That's how you'd read that. That means you have a total of n things, but you only care how a certain number of them are arranged. For example, in the Olympics we just had, you'd have, 8 people running in a race. We really could care less about 4 through 8. We just care who got the gold, silver, and bronze, right? So we only really care about the top 3. Okay, now if you're one of the other 8, you probably care how you finished, but if all we care is how many different ways could people finish with the gold, silver, or bronze medal, we would be doing an 8 permutation 3. Okay? 8 permutation 3. Now, like we had said, if I do 8 factorial, that tells me how many different ways all 8 runners were finishing, okay? If I divide that then by this n minus r, the 5 factorial, you know I just divided out? I divided out the 5 people I didn't really care about, okay? I only care about the first 3, so by dividing by 5 factorial, that gets rid of all the arrangements of the other 5 people, okay? So that's pretty cool. But a permutation, notice in each of these cases, when we're talking about permutation, we are looking at them in a specific order. Okay? We're looking at them in a specific order. It matters who got first, second, or third. Right? A combination, on the other hand, is where we're selecting a group. Okay? Earlier in the rounds, like in track and field and stuff, they do multiple heats, or in swimming too. And like the top 2 from the heat, it didn't matter if you finished first or second, as long as you were in the top 2, you got on to the next round. Okay? So that would be like the combination. We don't care what order they're in any order, we're just selecting a group. In that case, we might have 8 runners, and we're selecting 2 of them to move on to the next round. Okay? Yes?
So the combination is you have all these things to pick from, and you pick a certain amount of them, and it doesn't matter what order they're in. And then the permutation is where you have this amount of things to choose from, and you pick a certain number, but they have to be in a certain order.
Yes.
Okay.
So if I were to pick, 1, 2, 3, and then I pick, 3, 2, 1, those would be 2 different permutations because they're in a different order. But that would just be one combination because I still have the same 3 people. You know what I'm saying? It would only count as one. So actually, this is a good way because a lot of people mess up the formulas. They mix them up. You should always get a smaller number of combinations. All right? Because if order doesn't matter, then I could have the same 3 people and they could be in different orders. It doesn't matter. That still just counts as one. All right? Now, reading this would be read, we could say n choose. We'll use the word choose sometimes instead of combination, just to shorten it, okay? And choose r. So in our example, if we had 8 runners and we're just choosing 2 to go on to the next round, it'd be 8 choose 2. So you'll notice the formula just has one extra aspect of it, okay? And here's how it works. 8, remember, is the arrangement of all 8 runners. We divided by 5 factorial, or I'm sorry, in this case it would be 6 factorial, because those are the 6 runners we don't care about. We don't care what order they finished in, because they're not the top 2, okay? But then we have to do one more thing, because at this point we still have them in a specific order. So we divide now by, in this case, the 2 factorial, that r factorial. That gets rid of the different arrangements of those 2 people. Okay? And we're going to revisit this in Unit 2, but I just want you to see kind of how this is used in at least one application. Okay? So, any questions? Yes?
What's the parentheses n over r? Yeah.
That's another kind of notation for combinations. You may see that. I don't typically use it because it looks like either a 2x1 matrix or it looks like vector notation. It's actually the same notation that's used for a bunch of different stuff in mathematics. So that's why I don't use it a whole lot, but you may see it out there. Okay, good question. All right. So there's some application of factorials again that we'll visit a little bit more later on. Okay. All right. The last thing I want to look at is our sigma notation. Okay. Today we're kind of hitting three major topics that all kind of relate to sequences and series. And we'll start putting everything together as we move forward. Sigma notation or summation notation. This is called sigma notation because this symbol here, is the Greek letter sigma. Okay, it's capital sigma. Now, to read this, you can see here I have how I have this labeled. The sum, okay, the sigma stands for the sum from I equals 1 to n. So notice you put a starting point at the bottom. You have this variable that's going to show up in the expression here. Okay? And at the bottom, the I is called the index of summation. That's the thing that's kind of changing each time. It's just a variable that we're plugging in different values for. The 1 is the lower limit, and then the n on top is the upper limit. That kind of makes sense. Okay, so if we're taking the sum from 1 to 5, we're going to have 5 different things we're adding up. The first time we're going to plug in 1, then the second time we're plugging in 2 and 3 and so on. Okay? And the cool thing is you don't have to start at 1. A lot of times we do, but you could start anywhere and you could end anywhere. All right? But this is how we would read this. The sum from I equals 1 to n of a sub I. All right, so you see there, what does this look like? That a sub I. We saw that earlier, right? What do we call that? A sub I. When it was a sub n, that referred to the... Going back to the beginning, the sequence, okay? A lot of times we'll use these sums for a sequence, okay? For adding up terms of a sequence. Now, that's what we call a series then. If you're taking terms of a sequence and adding them together, now you have a series, okay? So, that's the notation that we're using there, okay? There are a couple of different properties. These aren't really terribly difficult ones, so we're just going to run through them kind of quick, okay? If you have a constant, this is sometimes, it's the simplest one, but sometimes it's the hardest one to really make sure we understand, okay? If you have a constant, in other words, notice the index does not appear. It's not CI or anything like that. It's just a constant. Then you just take that constant and multiply it by n. Okay? This is a nice one. If you have a constant inside of it, you actually can pull the constant outside. Can anyone think and tell me what property we're using to do that? It's the distributive property. All right? Think about it. We're adding up a whole bunch of stuff, right? And all of those things are being multiplied by c. So c would make it a common factor of all those things. So we can then use the distributive property to factor out that common factor and put it out in front of the sum. Okay? Another thing here, number 3 and 4 kind of go together. If you're adding two different things together inside a sum, you can separate it into two different sums. If you're subtracting, you can subtract them into two different sums as well. Okay? So I give you this example here because we could actually apply all these rules. I could split up the 3i and the 4. So I could make it the sum from I equals 1 to 5 of 3i plus the sum from I equals 1 to 5 of the constant 4. But then I could keep going, right? Here, this is a constant multiplied by my index. So what can I do with that 3? I can take it out, all right? I could rewrite this as 3 times the sum from I equals 1 to 5 of just I. Okay? And then if this is a constant 4, how could I rewrite that? 4,
For I, for 1. So just 4.
No, 5 times 4.
5 times 4, yeah, that constant 4 times the n, 5. Okay? So you see how rather than having to evaluate this 3i plus 4 5 different times, I already know half of it equals 20. And then this, it's just 1 plus 2 plus 3 plus 4 plus 5. And I multiply that whole thing by 3. Okay? So 1 plus 2 plus 3 plus 4 plus 5 is 15. So yeah, 3 times 15 plus 20 is 45 plus 20, so we've got 65. Okay? So if we're able to break it down a little bit, that makes life a little easier for us. Keeps the numbers smaller, less work to do. Okay? So, a series is one last term we'll close off the day with here. A series, I already mentioned, is just the terms of a sequence added together. Okay? The main term that we need to make sure we understand here is partial sum. Okay? A partial sum is the sum of the first however many terms of that series. Okay? So if I have the third partial sum, that's the first 3 terms. Okay? The 10th partial sum is the first 10 terms. So you'll notice here, using this notation here, the third partial sum would be the sum from I equals 1 to 3 of a sub I. Okay? The 10th partial sum would be the sum from I equals 1 to 10 of a sub I. Okay? So that's the basic idea here that we're dealing with. You'll notice here at the bottom we have this example finding the sum of a series. If we just need the third partial sum, and we have 3 over 10 to the I, it would be 3 over 10 to the first, plus 3 over 10 to the second, plus 3 over 10 to the third. Okay? So let's think about this. 3 over 10 is just a 0.3, right? What's 3 over 100?
0.03.
0.03. And 3 over 1,000?
0.003.
Yeah. Okay? So you put that together and you get 0.333, right? So this is kind of mind-boggling here. We have an infinite series. If you add up an infinite number of things, shouldn't you get infinity?
Yeah.
Well, it depends. Okay, that makes sense. But check this out. Look at the pattern that our sequence is taking so far. 0.3, 0.03, 0.003. If I keep doing that forever, what am I going to get?
0.3.
Yeah, yeah. And what does that equal? 1/3. Okay? It's pretty cool, huh? Alright, so give the independence practice, the required independent practice, a try this evening. Okay? There are more problems at the end of these notes than are actually required. Okay? So go back to the PDF of just the required ones to see what you got to do. Okay? Alright, have a great day, guys.